The National Electrical Code does not specifically require multiple grounding connections for metal vessels located in hazardous areas. However, Article 250.114, grounding and bonding of non-electrical equipment and metal piping systems, mandates the bonding of metal piping systems and other conductive materials that could potentially become energized. Furthermore, Article 501.16, bonding and grounding, requires the bonding and grounding of electrical equipment in hazardous locations to prevent the accumulation and discharge of static electricity. Providing multiple grounding connections for metal vessels in hazardous locations is recognized as good practice. This enhances the reliability of grounding and reduces the risks associated with static discharge and lightning strikes. The Institute of Electrical and Electronics Engineers Green Book, also known as IEEE Standard 142, which is the recommended practice for grounding of industrial and commercial power systems, advocates for multiple grounding connections for metal vessels in hazardous locations, stating that multiple grounding connections shall be provided for metal vessels in order to ensure that a low ground resistance path exists under all conditions. Factory Mutual, or FM, also suggests multiple grounding connections for metal vessels in hazardous locations, recommending them to reduce the risk of spark discharge and to provide a low resistance ground path. Process Industry Practices, or PIP, provides guidance on grounding and bonding in hazardous locations, recommending multiple grounding connections for metal vessels to improve grounding reliability and mitigate the risk of static discharge and lightning strikes. Multiple grounding connections can help to reduce the risk of static discharge by providing multiple paths for static electricity to dissipate. Multiple grounding connections can help protect against lightning strikes by providing a low resistance path for lightning current to flow to ground. In conclusion, while the National Electrical Code does not specifically require multiple grounding connections for metal vessels in hazardous locations, providing them is considered good practice for improved grounding reliability and reduced risk of static discharge and lightning strikes. The National Electrical Code, or NEC, provides a comprehensive framework for electrical safety, and understanding its requirements is crucial for ensuring safe installations. Here's a deeper dive into the relevant sections and related concepts. Grounding and bonding are fundamental principles in electrical safety, serving to minimize the risk of electric shock and fire hazards. Grounding creates a low impedance path for fault current to return to the source, enabling overcurrent protection devices such as circuit breakers and fuses to operate and clear the fault. Bonding ensures that all metallic parts are electrically connected, creating an equipotential plane that minimizes voltage differences and reduces the likelihood of dangerous touch potentials. Article 250 within the National Electrical Code covers the general requirements for grounding and bonding electrical systems. It outlines the rules for grounding electrode systems, equipment grounding conductors, and bonding of metal parts. Section 250.4 clarifies the general requirements for grounding electrical systems, including the need to ground electrical systems to limit voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines and to stabilize voltage to ground during normal operation. Section 250.24 details the requirements for grounding separately derived systems such as generators or transformers. It specifies how these systems should be grounded and bonded to ensure proper operation of overcurrent protection devices. Hazardous locations, as defined in Article 500 of the National Electrical Code, are areas where fire or explosion hazards may exist due to the presence of flammable gases, vapors, liquids, combustible dusts, or ignitable fibers or flames. These locations are classified based on the type and likelihood of the hazard, with different classes, divisions, and zones. Article 501 specifically addresses hazardous locations classified as Class I, which are areas where flammable gases or vapors may be present in the air in quantities sufficient to produce explosive or ignitable mixtures. Within Class I locations, divisions or zones further categorize the risk. Division 1 locations are those where ignitable concentrations of flammable gases or vapors are likely to exist under normal operating conditions, while Division 2 locations are those where ignitable concentrations are likely to exist only under abnormal conditions. Zones are an alternative classification system used internationally and gaining acceptance in the National Electrical Code. Zone 0 locations are those where ignitable concentrations of flammable gases or vapors are present continuously or for long periods. Zone 1 locations are those where ignitable concentrations are likely to exist under normal operating conditions, and Zone 2 locations are those where ignitable concentrations are likely to exist only under abnormal conditions. In hazardous locations, electrical equipment must be specifically designed and approved for use in the particular class, division, or zone. This equipment is typically explosion-proof, intrinsically safe, or non-incendive. Explosion-proof equipment is designed to contain an internal explosion and prevent the propagation of flames or sparks to the surrounding atmosphere. Intrinsically safe equipment is designed to limit the energy available to a level that is too low to ignite a flammable atmosphere. Non-incendive equipment is designed not to produce sparks or thermal effects capable of igniting a flammable atmosphere under normal operating conditions. Article 501.16, mentioned previously, emphasizes the importance of bonding and grounding in hazardous locations to prevent the accumulation and discharge of static electricity. Static electricity can be generated by various processes such as the flow of fluids through pipes, the movement of machinery, or the presence of personnel. If static electricity accumulates on conductive objects, it can discharge in the form of a spark, which can ignite a flammable atmosphere. Bonding and grounding provide a path for static electricity to dissipate safely to ground, preventing the buildup of static charge and reducing the risk of ignition. The IEE Green Book, officially known as IEE Standard 142, recommended practice for grounding of industrial and commercial power systems, provides detailed guidance on grounding practices for various types of electrical systems. It covers topics such as grounding electrode systems, equipment grounding conductors, bonding, and surge protection. The Green Book recommends multiple grounding connections for metal vessels in hazardous locations to ensure a low ground resistance path exists under all conditions. This helps to minimize ground impedance and reduce the risk of voltage rise during fault conditions or lightning strikes. Factory Mutual, or FM, is a commercial and industrial insurance company that also provides engineering and testing services. FM Global provides recommendations and guidelines for various aspects of industrial safety, including electrical safety and grounding. FM Global loss prevention datasheets provide specific guidance on grounding and bonding practices for hazardous locations. These datasheets recommend multiple ground connections for metal vessels to reduce the risk of spark discharge and provide a low-resistance ground path. Process Industry Practices, or PIP, is a consortium of process industry companies that develops and publishes recommended practices for engineering and construction. PIP provides guidance on grounding and bonding in hazardous locations, recommending multiple grounding connections for metal vessels to improve grounding reliability and reduce the risk of static discharge and lightning strikes. Static discharge is the release of static electricity when two objects with different electrical charges come into close proximity. In hazardous locations, static discharge can be a significant ignition source, as the spark produced can ignite flammable gases, vapors, or dusts. Multiple grounding connections can help to reduce the risk of static discharge by providing multiple paths for static electricity to dissipate. This minimizes the buildup of static charge on conductive objects and reduces the likelihood of a static discharge event. Lightning protection is another important consideration in hazardous locations, particularly in areas where lightning strikes are frequent. Lightning strikes can generate extremely high currents and voltages, which can damage electrical equipment and ignite flammable atmospheres. Multiple grounding connections can help to protect against lightning strikes by providing a low-resistance path for lightning current to flow to ground. This helps to divert the lightning current away from sensitive equipment and reduce the risk of ignition. In conclusion, while the National Electrical Code does not specifically require multiple grounding connections for metal vessels in hazardous locations, it is recognized as good practice to provide them for improved grounding reliability and reduced risk of static discharge and lightning strikes. Implementing multiple grounding connections is a proactive safety measure that can help to prevent accidents and protect personnel and property in hazardous locations. Additionally, adhering to the recommendations of organizations such as the IEE, Factory Mutual, and process industry practices can further enhance the safety and reliability of electrical systems in hazardous environments. When designing and installing electrical systems in hazardous locations, it is essential to consult with qualified electrical engineers and contractors who have experience in this specialized area. They can assess the specific hazards present at the location and recommend appropriate grounding and bonding practices to ensure the safety of the installation. Moreover, regular inspections and maintenance of grounding and bonding systems are crucial to ensure their continued effectiveness. This includes checking ground connections for corrosion, tightness, and continuity and testing ground resistance to ensure it meets applicable standards. Grounding electrode systems should be inspected periodically to ensure that they are in good condition and provide a low impedance path to ground. Bonding jumpers should be checked for proper installation and tightness. In addition to the technical aspects of grounding and bonding, it is also important to train personnel who work in hazardous locations on the hazards associated with static electricity and lightning strikes. They should be trained to recognize potential sources of static electricity and to avoid activities that could generate static charge. They should also be trained on the proper procedures to follow in the event of a lightning strike. Overall, ensuring electrical safety in hazardous locations requires a comprehensive approach that encompasses proper design, installation, maintenance, and training. By adhering to the National Electrical Code, industry best practices, and common sense safety principles, it is possible to minimize the risks associated with electrical hazards in these challenging environments. Remember to always consult with qualified professionals and stay informed about the latest safety standards and regulations. Electrical safety is a continuous process that requires vigilance and a commitment to excellence. Let's now expand on specific grounding and bonding techniques applicable in hazardous locations. Firstly, consider the grounding electrode system. The National Electrical Code Article 250 dictates acceptable grounding electrodes. These electrodes can be metallic water pipes, ground rings, rods, and plates. In hazardous locations, it is crucial to ensure that the grounding electrode system provides a low impedance path to earth. Multiple grounding electrodes, as recommended by the IEE Green Book, significantly enhance the reliability of the grounding system. This redundancy ensures that even if one ground electrode fails, the system maintains a sufficient grounding path. Secondly, equipment grounding conductors, or EGs, play a vital role. These conductors provide a low impedance path for fault current to return to the source, enabling overcurrent protection devices to operate effectively. In hazardous locations, the size and material of EGC are critical. The National Electrical Code specifies the minimum size of EGC based on the rating of the overcurrent protection device. However, in hazardous locations, it is often prudent to use larger EGC to further reduce impedance and enhance safety. Copper conductors are generally preferred due to their low resistance and corrosion resistance. Thirdly, bonding jumpers are essential for ensuring electrical continuity between metal parts. These jumpers connect metal enclosures, conduit, and other metallic components, creating an equipotential plane. In hazardous locations, bonding jumpers must be securely installed and adequately sized to carry fault current. The use of exothermic welding, also known as CAD welding, is highly recommended for making permanent, low-resistance connections. Exothermic welding creates a molecular bond between the metals, providing a reliable and corrosion-resistant connection. Fourthly, surge protection devices, or SPDs, are crucial for protecting electrical equipment from voltage surges caused by lightning strikes or switching transients. In hazardous locations, SPD must be specifically rated for use in the particular class, division, or zone. These SPD should be installed at the service entrance and at critical equipment locations to provide comprehensive surge protection. Fifthly, intrinsically safe systems require special grounding and bonding considerations. Intrinsically safe circuits are designed to limit the energy available to a level that is too low to ignite a flammable atmosphere. However, proper grounding and bonding are still necessary to ensure the integrity of the system. Intrinsically safe barriers must be properly grounded to prevent the buildup of static charge and to provide a return path for fault current. Sixthly, regular inspections and maintenance of grounding and bonding systems are essential. These inspections should include visual checks for corrosion, loose connections, and damaged components. Ground resistance testing should be performed periodically to verify the effectiveness of the grounding system. Any deficiencies should be promptly corrected to maintain the safety and reliability of the installation. Seventhly, documentation is crucial. Maintain accurate records of all grounding and bonding installations, including the location of grounding electrodes, the size and type of conductors, and the results of ground resistance tests. This documentation can be invaluable for troubleshooting and future maintenance. Eighthly, consider the specific hazards present at the location. The type of flammable material, the likelihood of its presence, and the operating conditions all influence the grounding and bonding requirements. A thorough hazard assessment should be conducted to determine the appropriate level of protection. Ninthly, always consult with qualified electrical engineers and contractors who have experience in hazardous locations. They can provide expert guidance on the design, installation, and maintenance of grounding and bonding systems. Tenthly, stay up to date with the latest codes and standards. The National Electrical Code and other relevant standards are constantly evolving. It is important to stay informed about the latest requirements to ensure compliance and maintain a safe electrical installation. Now let's elaborate on static electricity in hazardous locations. Static electricity is the buildup of electrical charge on the surface of an object. This charge can be generated by various mechanisms, including friction, induction, and separation of materials. In hazardous locations, static electricity can be a significant ignition source. If the static charge accumulates to a sufficient level, it can discharge in the form of a spark, which can ignite flammable gases, vapors, or dusts. The amount of energy required to ignite a flammable atmosphere varies depending on the specific material. Some materials, such as hydrogen and acetylene, are easily ignited by even small sparks. Other materials, such as methane and ethane, require more energy to ignite. The minimum ignition energy, or MI, is the minimum amount of energy required to ignite a flammable atmosphere under specific conditions. The MIE is an important parameter to consider when assessing the risk of static discharge in hazardous locations. Several factors influence the generation and accumulation of static electricity. Firstly, the type of materials involved. Some materials, such as plastics and rubber, are more prone to generating static electricity than others. Secondly, the surface conditions. Rough surfaces tend to generate more static electricity than smooth surfaces. Thirdly, the humidity. Low humidity environments promote the buildup of static charge. Fourthly, the speed of separation. Rapid separation of materials generates more static electricity than slow separation. Fifthly, the presence of conductive objects. Conductive objects can accumulate static charge if they are not properly grounded. Several measures can be taken to mitigate the risk of static discharge in hazardous locations. Firstly, grounding and bonding. As discussed previously, grounding and bonding provide a path for static electricity to dissipate safely to ground. Secondly, humidification. Increasing the humidity can reduce the buildup of static charge. Thirdly, antistatic additives. Antistatic additives can be added to materials to reduce their tendency to generate static electricity. Fourthly, conductive footwear. Personnel working in hazardous locations should wear conductive footwear to prevent the buildup of static charge on their bodies. Fifthly, conductive clothing. Conductive clothing can also help to prevent the buildup of static charge. Sixthly, avoiding activities that generate static electricity. Activities such as rubbing, brushing, and spraying can generate static electricity. These activities should be avoided in hazardous locations whenever possible. Now let's delve into lightning protection in hazardous locations. Lightning strikes can pose a significant hazard in hazardous locations, particularly in areas where lightning strikes are frequent. Lightning strikes can generate extremely high currents and voltages which can damage electrical equipment and ignite flammable atmospheres. A lightning protection system is designed to protect structures and equipment from the harmful effects of lightning strikes. A typical lightning protection system consists of several components. Firstly, air terminals, also known as lightning rods. These are installed on the roof of a structure to intercept lightning strikes. Secondly, down conductors. These provide a path for lightning current to flow from the air terminals to ground. Thirdly, grounding electrodes. These provide a low impedance path for lightning current to dissipate into the earth. Fourthly, surge protection devices, or SPDs. These protect electrical equipment from voltage surges caused by lightning strikes. When a lightning strike occurs, the air terminals intercept the strike and direct the current through the down conductors to the grounding electrodes. The grounding electrodes dissipate the lightning current into the earth, minimizing the voltage rise on the electrical system. Surge protection devices protect sensitive equipment from voltage surges that can propagate through the electrical system. The design and installation of a lightning protection system should be performed by qualified professionals who have experience in this specialized area. The lightning protection system should be designed to meet the requirements of applicable codes and standards such as National Fire Protection Association 780 standard for the installation of lightning protection systems. In hazardous locations, special considerations must be taken when designing a lightning protection system. Firstly, the air terminals should be located away from areas where flammable materials are stored or processed. Secondly, the down conductors should be routed away from sensitive equipment. Thirdly, the grounding electrodes should be located in areas with low soil resistivity. Fourthly, surge protection devices should be specifically rated for use in hazardous locations. The effectiveness of a lightning protection system depends on proper installation and maintenance. The system should be inspected periodically to ensure that all components are in good condition and that the connections are tight. Ground resistance testing should be performed regularly to verify the effectiveness of the grounding system. Any deficiencies should be promptly corrected to maintain the protection provided by the system. In addition to a lightning protection system, other measures can be taken to reduce the risk of lightning strikes in hazardous locations. Firstly, grounding and bonding. As discussed previously, grounding and bonding provide a path for lightning current to dissipate safely to ground. Secondly, surge suppression. Surge suppression devices can be installed on electrical equipment to protect it from voltage surges caused by lightning strikes. Thirdly, shielding. Shielding can be used to protect sensitive equipment from electromagnetic interference caused by lightning strikes. Fourthly, weather monitoring. Weather monitoring systems can provide early warning of approaching thunderstorms, allowing personnel to take precautions to protect themselves and equipment. Remember, the design, installation, and maintenance of electrical systems in hazardous locations demand meticulous attention to detail and adherence to stringent safety standards. The goal is to mitigate the risks associated with flammable materials, static electricity, and lightning strikes, ensuring a safe working environment for all.